Hey guys, we're going to start chewing our way through the rather enormous topic of chemical change for grade 12s. There's a whole bunch of different sections. There's rates and extent of reaction, equilibrium, acids and bases, electrochemistry, and then stoichiometry, which kind of finds its way into everything. So there's a lot to cover. We're going to kick off with rates. Now just remember that these videos are not meant to be teaching you from the ground up. Hopefully you've had some great teaching at school on that and covered the topics before. This is just revision, so we're going to be blitzing our way through and just giving you hints, tips, highlights, some easy ways to remember things or easy ways to process them. Always remember that you can pause the video, rewind, and watch again if it goes a little bit too fast. Okay, so rates of reaction. What is the rate of reaction? Bunch of different ways to understand it or define it. Probably the best way of saying it is the change in concentration, the rate of change in concentration of the products of a reaction, or something along those lines. And it all starts with collision theory. Collision theory is nothing to do with momentum. That is a whole other story altogether. It's about atoms and molecules colliding with each other, bumping into each other. So let's take a hypothetical reaction where A reacts with B to produce C. So it could be hydrogen plus oxygen gives you water, or hydrogen plus chloride, chlorine gives you hydrogen chloride, or something along those lines. And we've got a container with our A's and B's bouncing around inside here. And in order for A to react with B, they have to actually meet. I often think of it like romance, you know. And to fall in love, you've got to meet someone. You can't just fall in love with a random imaginary person. Well, I suppose you could, but that's a bit sad. Anyway, you've got to actually meet them. So let's picture ourselves in let's take it back a bit. So instead of rather than a club kind of scenario, let's go back a couple hundred years to one of those ballrooms where they swan around the dance floor like this. And the lords and ladies of the land come to find a suitable suitor. Basically, they're trying to get hitched. So A and B go for a little dance around the dance floor. And they're dancing, and she realizes, oh, he didn't brush his teeth, this is bad, and she just can't wait to get out of the moment. And so that was not a successful collision, all right? Meanwhile, other side of the dance floor, Albert and Bertha are dancing, and man, there is just like magic in the air, the music is playing, it's just a sweet, sweet, sweet moment, and they fall in love, and they become an item, Mr. and Mrs. Albert, Bertha, Frankenstein, or whatever you might want. So that was what we would call in chemistry an effective collision. Okay, an effective or a successful collision. So when our hydrogen and oxygen react together to become water, that's exactly what went down. The hydrogen bumps into the oxygen, hey, they fell in love, and they made water. Okay, so what constitutes an effective collision in chemistry? In human relationships is hectically complicated. You know, do you find them attractive? Do you share a sense of humor? Does he smell nice? You know, all those kinds of things. But for molecules, it's just dead simple. It's literally, are you going fast enough? That's all they're interested in. Is sufficient EK. It's all to do with activation, energy, and that kind of stuff, which I'm sure you've got some understanding of. There is one other very practical thing, which once again actually ties in with the whole dance floor kind of analogy, and that is correct orientation. They literally have to bump into each other the right way around. You know, so imagine you're at a particular party or ball or whatever it is, and your Prince Charming happens to be there, or your Miss Wonderful, and you meet them. You actually bump into them, but you didn't get to meet them properly because you bumped into them behind you. Like, you know, the moment passed, and you'll have to wait till the next occasion to meet them properly. And same thing can happen with the molecule. They can bump into each other the wrong way around, nothing's going to go down. So it's got to be the correct way around. So it's pretty random, that whole thing, but it is important. So that is what collision theory is all about. Effective collisions, very important little phrase there that you do well to refer to. Okay, so now they often ask you to make use of collision theory in explaining stuff, how a certain factor will affect the rate of reaction, you know, whether you're heating it up or adjusting concentration or something like that. So what I want to do is draw you a little flow chart that helps to break down how to use the collision theory, how to explain stuff and actually get all the marks, because a lot of it's quite logical, a lot of the factors are logical, and you'd be able to get the answer as to whether it's going to speed the reaction up or slow it down. It's not rocket science, you know what I mean? What was I saying? The trick is being able to get all the marks. Okay, so sorry, I had a mental freeze there for a moment. So one of the key things that I'm sure you're all saying, if I asked you the question, how can you make a reaction go faster? You're going to say, heat it up. Okay, so temperature is definitely an important factor. Another one is the concentration of a solution, which is kind of related to two other things. They're also pressure and volume. That would be for a gas, really, because the more pressured it is, the more concentrated it is, and volume, by reducing the volume, you increase the pressure, obviously. So that's another thing that can speed up or slow down a reaction, depending how you fiddle with it. Surface area, or state of division, is another one. And I'm sure you've done reactions with calcium tablets, and you have one whole one and one broken one and one crushed one, that kind of thing. And then catalyst. And the ultimate objective is to explain the effect of each of those on the rate of reaction. So what I want to do is give you some steps to argue through. Your penultimate point, in other words, your second last point, is always going to be about effective collisions, because without effective collisions, we don't have a reaction. So whether you get more or less effective collisions is going to affect the rate. We know that effective collisions is about sufficient, sorry, excuse my handwriting, energy on one hand, and correct orientation on the other hand. So let's have a look at concentration to start with. When you increase the concentration of a substance, picture it. There's your beaker, it's all got all the little molecules bouncing around inside. It's like a little dance floor with people dancing on the dance floor. We up the concentration. We're putting more people on the dance floor. Obviously the reaction rate is going to go up, but why? We're not making people bump into each other the right way around. That's still as random as if it was before. We actually, in this case, haven't increased their energy either. They're still moving at the same speed, so we haven't made them go any faster. But there is another factor, and this one is purely a function of numbers. What we have done is we put more people on the dance floor, put more molecules into the container, therefore increase the number of collisions, just because of the fact that there are more particles. I'm going to use blue for that. Okay, so in your argument you could say when Tabo increases the concentration of his acid, there are more moles per unit volume, or more molecules per unit volume, which leads to more collisions. Therefore, there will be more effective collisions. Therefore, the rate of reaction will increase. And there it is. Okay, so there's your marks. Surface area. When you increase the surface area by breaking something down, what you're doing is the same thing. You're enabling more collisions. They're still going to be bouncing into each other randomly and at the same speed, so you haven't affected those two. But you have once again led to more collisions, basically because the substances are more exposed to each other or have greater access to each other. Those kind of words are what you would use to explain that, which leads to more collisions, which leads to more effective collisions, which leads to a greater rate of reaction. Okay, getting the idea? Temperature is an interesting one because it actually has a double whammy effect. Obviously, we're making the particles go faster by increasing them, or increasing the temperature. So EK rises, or they're going faster. And that does two things. First of all, it also means more collisions. We've changed the music from Bach to Bon Jovi. No, that's shocking. Bieber? It's even worse. Okay, my brain is definitely not on the right planet today. Okay, but some awesome hip fast music. So the beat has increased and now people are moving faster. I wish I could think of the band names when I needed them. So the dance floor has completely changed the atmosphere from being swirling around, people are now rocking and they're going to be bumping into each other more often. And not only that, when they do bump into each other, because they're going faster, they're more likely to have a successful collision. So not only has the music changed, but he's now got some breath freshener and he's brushed his hair or something like that. So it's more likely to succeed because there's greater energy. So both of those lead to more effective collisions and a greater rate. Okay, and lastly, catalyst. Interesting one. What does a catalyst do? Speeds up the reaction. Okay, that's first thing. It doesn't react itself, but what it does, is it lowers the EA, and that is the key functionality of a catalyst. Is it lowers the activation energy. In other words, it hasn't affected any of these other things. It hasn't affected the number of collisions. Hasn't affected the orientation. It hasn't even affected their speed. But what it has done is it means that when it does collide, it's going to happen more easily. And what that is like you see this most beautiful girl on the other side of the dance floor and you think, oh my gosh, I wish I could go and talk to her. I'm just feeling so nervous. And then you chat to your mate about it and he says, I know her, like she lives just down the road from me. We were at junior school together and she's a good mate of mine, let's go and chat. And so he becomes your wingman. He is the catalyst that might lead to some magic, you'll see. Or wingwoman, change the scenario, that's the idea. So it lowers the activation energy, thereby making it more likely for something to happen or easier for something to happen, leads to more effective collisions and therefore a faster rate of reaction. So that's a quick map. Have a look at that, take a photograph if you want, and that'll help you to break it down into points. Okay, whilst we're thinking about all of that, let's move on to the first of our graphs. This section has quite a few graphs between this and equilibrium, there's a bunch of them. What we're going to have a look at first is Maxwell Boltzmann graphs. They are distribution curves. In other words, they tell us about the makeup of a population of stuff, effectively. So what it is, it's telling us how many particles have a certain energy in our little sample. So this is Maxwell Boltzmann. Max Boltz, I'll just put for short. Okay. So when I say distribution, remember at junior school you probably did, shoe size graphs or something like that, a histogram, and you had something like this. Most people had size 4, and da-da-da-da. Okay, so it's a similar kind of concept. Let's have a look. What we're looking at is the spread of energies, kinetic energies of the particles. How many particles have a certain energy? And what it typically looks like is that. So it's a bell curve-ish kind of thing, slightly skewed. Very few particles have no energy at all, or there wouldn't be any, but there would be some have a little bit of energy. Most have a moderate amount of energy, and some have lots and lots of energy. And somewhere over here, there'll be a cutoff point, and that is our activation energy. And any particle above that will be able to react. It's got sufficient energy to react. Okay, so that could be like, a little analogy for this one, it could be like the spread of salaries in a particular population, say in South Africa. Some people are not earning very much at all. Most people are earning a moderate salary. We wish the employment rate was higher, but anyway, let's just take it as employed people. And some people are earning lots and lots and lots and lots of money. And this cutoff point could be, say, a holiday to Mauritius is the usual example. And so people are earning more than a certain amount can afford to go to Mauritius on holiday. Fantastic. So let's look at what happens now. What you would do with a graph like this in an exam, they may give you two before and an after, or you may even have to plot it yourself. So what we would have is something like this, where this is an initial temperature. And we're going to first of all look at what happens when you change the temperature. If T2 is greater than T1, what does the second graph look like? Well, we know by increasing the temperature, things are going faster. So we're increasing the kinetic energy. So what does that do to the graph? Well, back to the analogy, the guy who's begging at the side of the road, well, he might get lucky and get a few more better tips from more generous people. What's happened in the economy is that people's salaries have gone up. The economy has improved. And so the moderate salary people have also shifted to get a slightly higher salary. And the guys who are earning lots are also earning more than they were. So everything shifts to the right because energy has increased. Salaries have increased, as it were. Now, at the same time, we haven't increased our population. So we can't just make more people out of nowhere. This has to spread out over a larger area, and therefore the peak will in fact be slightly lower than it was before, but it will spread out. So something along those lines. So there's your T2, further right and lower than T1. And what happens to our activation energy is still the same. So in terms of people going to Mauritius, what happens is there's a whole bunch more people going to Mauritius now because they can afford it. Because lots of people are earning more money. So an increase in temperature is a bit like some sort of economic boom, and things take off and everyone's more well to do. So that's the first scenario. The second one, you always start with, I'm going to be able to rub this off accurately. The second scenario is a change in concentration. So the initial graph is always the same, as I said, and this time what's happening, let's say that it starts at initial concentration and then the concentration is increased. So there's our starting curve, there's our activation energy, and we're going to look at a case where C2 is greater than C1. Okay, concentration now has increased. Those were the people who could afford to go to Mauritius. What happens now when the concentration goes up? Well, when you increase the concentration, you're not affecting the energy. So we're actually not shifting it to the right at all this time. But what we are doing is we're making more moles, or putting more moles into the space. So the amount actually goes up this time, and therefore the graph is going to look same sort of shape, should have the same peak. I haven't done it perfectly, but that's the idea. C2 is higher in this case than C1. Once again, ticket sales to Mauritius go up, not because everyone's richer, just because there's more people. Okay, so this is a bit like a population boom. This is, comparing 2012 to 2017 or something like that, and suddenly in 2017 there's a whole lot more working people in the workplace, and so the number of people able to go to Mauritius goes up because there's more people around. Okay, and the last graph to look at is what happens when we add a catalyst. Now, as we said, a catalyst doesn't directly affect the speed of the particles. It doesn't affect the number of particles. So in fact, we're not going to change this curve at all. But it does make the reaction go faster. So you've got to think, well, how on earth does that happen? Okay, here's our axis. Whoa. I can dry it over. Try again. There we go. Okay, it's a bit of a struggle. So there's our lucky people going off to Mauritius. But things are extremely lucky now. When we add a catalyst, what happens is, remember the key phrase, is it lowers the activation energy. So that is what we've changed. Here's our activation energy, that's where it was. We've now lowered it, which means it ends up somewhere over here. That is the catalyzed activation energy. So once again, we've got a whole stack more people going to Mauritius. Yay, yay, yay. Why? Because the activation energy is lower. In other words, what's happened? They've dropped the price. It's some sort of special offer. And instead of being 10,000 Rand, it is now only 2,000 Rand. And we can all go to Mauritius. Okay. So that's the kind of idea. So those are your Maxwell Boltzmann graphs. You've got to be able to understand them and introduce collision theory alongside of some of those. So do some practice with that. Next graph to look at. Well done if you are still with me. Stop and have a breather if you need one. The next graph is what we call a reaction progress graph, or an energy profile graph. So still looking at energy, but this time in a different way. One way of understanding the difference between these two graphs, that one that we just looked at, was looking at a particular moment. It was a snapshot. So just like a camera, you could take a snap of your particular chemical and it would analyze all the little molecules and work out how much energy they have. Imagine you could do that. That would be so cool. And it would plot you a graph of how many particles have so much energy. The energy now, with this reaction progress graph, or energy profile, is now looking at the energy or enthalpy versus time. So this is more of a movie, okay? It's telling us the story of how this reaction went down as time went by. So we'd start with reactants and say products down there. Let's take a non-laboratory kind of scenario, seeing as it's winter, making fires. Okay, I'm getting my boys to learn how to make fires with not just firelighters, but twigs and sticks and newspaper and rustic things like that. Good old Boy Scout style. So what we'd have is we'd have the wood, but the wood doesn't just go and turn into flames and give us energy and then become ash. You have to nurture that flame. So you have to add newspaper and then some little twigs and then some sticks and then some bigger sticks, and eventually the log itself is going to catch light. And once you're there, then you have one, and the fire is on a roll. And it's going to end up giving off a whole lot more energy than you had to put in the first place. Now obviously that amount of energy that we had to put in, you're probably happy with, I hope, that is the activation energy. When it gets to that point there, then it's become activated. So you can think of it as the activated complex, where a complex is just a mixture of stuff. Okay, so it's the mixture, the wood and the oxygen, all ready to rock and roll with a bit of petrol, and it's gonna react and give off a whole lot more energy than it required in the first place. Now, overall, in this particular case, energy was released. That was the change in enthalpy, as we say, and that energy exited the system. It's an exothermic reaction. Heat is given off. The weird thing about it is that delta H is actually negative. So you are standing by the fire and it's getting really warm and hot, and yet the delta H is negative. It's like, what? It's an upside down thing, because it's not from your point of view, it's from the poor log's point of view. The logs are there churning out their energy. They are giving, they are losing energy. You are the one receiving the energy. So it's not from your perspective, it's actually from the reactant's perspective. And that's why delta H is negative for exothermic reactions and positive for endothermic reactions, which would obviously be the other way around. Now what happens when we add a catalyst? Reduces the activation energy. So the activation energy is going to come down, therefore creating an alternative energy path which would look something like that. And textbooks will one day make it accurate and actually show that it happens in less time. So, but if you draw it to there, they're not going to mark you wrong. But this is a catalyzed activation energy. Just got to draw a dotted line, something along those lines. So it's not technically hard. These ones, you might have some values that you'll have to read and do a calculation for the delta H or work out what the activation energy is. But hopefully you know the way around that graph. Okay, we're nearly there. The last section is the extent of reaction. And again, there's more graphs here. The extent of reaction is not how fast the reaction goes, but how far it goes. And extent of reaction is measured by, for example, the most common one is collecting gas. So you'll have some sort of apparatus. Let me see how maybe I can draw something. Okay, so we'd have, say, acid with our metal that was put in there. You have a delivery tube, which is into a nice bowl of water. I work on my artistic skills. And there we go, there's some water. And then we would have some kind of catchment. It could be a measuring cylinder, would be quite rustic. A burette would be more accurate. And what happens is that is initially full to the brim of water. There's no air in there at all. And as the bubbles come through, they displace the water. Hence the method is called a displacement method. Okay. And so we can measure the volume of gas that is produced by this particular reaction. And we would usually do it with a stopwatch so that we can, looks like an Ewok, and that would then be something that we can plot on a graph, for instance, like this. There's V versus T, and we'd say as time went by, the graph went up like that, and eventually leveled off. And then we would have comparisons. So often in exams, this is the kind of question that comes up. They will put it in the context of an experiment. You'll have to also understand independent variable and dependent variable, which we'll go through when we do a worked example. But you would say, right, for example, that was the first experiment. Then they changed magnesium ribbon to magnesium powder, and we would expect it to go faster, obviously. But if it was the same mass, it should get to the same place, and we would end up with a second graph that might look something like that. So that is extent of reaction. Sometimes there are values, you have to read them. Other times it's just sketches, it's about shapes and comparisons and that kind of thing. But all relating collision theory, rates, etc., etc. I think that about wraps it up. So, yeah, one other thing to say is just stoichiometry. They could well bring in some stoichiometry here, so have a look at that video just to get your head around n equals m over m and c equals n over v, and bring them all together to moles and all that kind of stuff. But otherwise, have a little breather, and then I'm going to go through a worked example shortly.